So welcome to my class. Today we will start with SI based quantities. SI based quantities. So there are basically SI based quantities. There are a bunch of ideas you need to understand SI based quantities. We have base quantities, seven base quantities, mass, time, distance, Kelvin, Candelia, charge, and mole. These all other quantities in the world are based upon these quantities. Okay. Next we have these the all of these can be derived like this is gram, kg, seconds, meter, k, c, ci, mole, Avogadro number particle or just mole like this, and Candelia and I don't know about this one. I will revise this. This gives derived quantities. We also have bunch, all of these come from here, all these come from the above. All of these come from the above. Derived quantities, we have like let's say force, so this will use quantities from here, kg, ms minus 2, or force for ma, f. So it uses base quantities of mass and acceleration. This is a vector because it has a direction of force acts in a direction, and it has magnitude, which is basically its units, which is Newton meter, which is Newton, sorry. Next we have vector, magnitude. Then we have something like time, which is a scalar quantity. Up to vectors we have things like vector, force, magnitude, and Newton. Vector quantities act in a direction, so you can have like two different quantities like this. We will use head to tail rule to find out the resultant, which basically is how much force total that acts that isn't zero. So 5 Newton, 3 Newton. So head to tail, the head of the first, the tail of the second. So it will be like this, because it follows the tail of this and the head of the first and the tail of the second. So it will be used Pythagoras theorem, which is 3 square plus 5 square. Let me do the math. Which will be 34 or 5.83 Newton. We also have like if we have vectors at an angle. So this about here vectors at an angle. This will be called resolving vectors as a topic. It relates back to like resolving vectors at an angle, which could have let's say we have five. We have a direction like this. Let's say it's 110 degree. So we have a force acting like this. So let's say here it is 50 degree and here it would be 60 degree. So 50 degree we would have a vertical horizontal component which would be cos 50. Let's say the angle would be cos 50 and the force is 10 Newton. So we have this. No, actually let's say we have force like this, 50 Newton acting at an angle of 60 degree. So we will do this. We will draw a right angle like this and 60 degree. Let's say 60 degree. This is actually not 60, let's say 60 here. This is 60 degree. An angle is acting like this. So we will have uh, cos here, cos and sine x and cos y. So this is 10 Newton. So we have 60 cos 10 is equal, let's do the math. No, this is actually opposite. Sorry, I'm so absent minded. 10 cos 60. This will be 5 Newton in the horizontal direction. In the vertical direction we will have sine 50 equals 7.6. So we will also have a Pythagoras rule, like if you have an angle like this, so we will let's say here. So this would be head of the first, tail of the second, and third. So it will be like this. So this will have Pythagoras. Oh, this will be parallelogram method. So 5 Newton here, 5 Newton, 6 Newton, 10 Newton. So we will have 10 Newton square, 10 square, 6 square, 5 square. You will have 161. So if we count this, like here we have a branch of SI based quantity. These will be measured using uh, uncertainty, accuracy, and precision. No, let's do measurements. These would be measurement topic. Measurements. This would have accuracy and precision plus, and this also is linked here, like these two go hand in hand, like they are related in the way that they basically complement uncertainty, where that the uncertainty is caused by less accurate, less precise or less accurate values uncertainty, which also would have zero systematic error and surround environmental error. So we will see next systematic and environmental error. Systematic might be zero error, like the error that basically scales like this. So the zero over here is kind of blocked, it's not clearly being viewed, so that can be a problematic thing. Zero error and environmental error may be human reaction time while taking time based measurements. Systematic and environmental error, human reaction time while taking time based measurements. Human reaction time while taking time based measurements, like if a human basically takes it like a 0.5 seconds later or 0.1 second later, 1 millisecond later, like against actual, like the actual time something started, like we have something above falling and basically it takes 0.1 seconds. So yeah, this is human reaction time error, or it could be errors in measurement error. We would have errors like environmental errors in such as temperature being different, there being some temperature or something like that. In zero error, systematic error, we also have other errors where the other errors where equipment isn't working properly. In accuracy and persistency, we have basically, let's say, accuracy and persistency, we have something like 0.1 plus, let's see, we have a value of a true value of 110 Newton. So let's say we get a value of, when we measure it using some kind of scale, we get 9.1 Newton, then it is accurate. But if we get 8 Newton, 8.5 Newton, 8.6 Newton, 8.7 Newton, so these are not accurate while they are precise because they are close to each other but not close to the true value. So we have some formulas we have to use, like uncertainty, like we have 0.1 Newton. Let's say we have like 10 meter is the true value plus uncertainty of 0.1 meter, uncertain plus we have time t true value of 10 seconds plus 0.05 seconds. So if we have to take a percentage of this percentage uncertainty, then we will divide 10, then we will try 0.10 by 10 and multiply by 100, and 10 by 0.05 and 100. and add the values together that come. So 1% uncertainty here, in percentage uncertainty 1% plus and 1 over 0.5 percentage. So we add them together and we get 1.5 percentage. So we also have fractional uncertainty, that will basically be it in fractions. Fractional uncertainty plus true uncertainty, which is actually the total value that comes, like if you have let's say we have we added like 9.9 divided by 9.95, and then we will get whatever we get here, 9.9 9.95, we got 0.0999. So it would be 10, whatever let's say we have uh, 10 over 10, we get 1 plus minus 0.1. So this will be basically the true uncertainty. So this topic is done. We will next now move on to kinematics, which is of course related here by time and distance and displacement. Kinematics, study of motion. So yeah, we have kinematic study of motion. So we will have something like kinematic study of motion. We will have study of things like displacement and distance are the main core ideas. Distance plus displacement. Distance is basically like if we have like a map, this is the total distance this area has, like let's say this is actually like we use like we calculate the area here, surface area, and it's like 1 meter square. But displacement will basically be like if we take this point and this point, and how much displacement basically is here, like how much direct distance there is like in our direction. So this direction here, it's like 250 meters. So this is displacement. Kinematics displacement. So next we use these two with time. By time we get velocity. If you do distance, we get speed. Speed is a scalar, while distance is a velocity is a vector. Speed scalar, velocity vector. Displacement, distance plus displacement. So we basically from here, if we divide again by time, we will get acceleration. Acceleration acceleration, which is rate of change of velocity, while velocity is the displacement over time, and distance is distance over time, displacement over time plus. So we have this. Next we have graphs for everything. Displacement, let's just draw them here. We have like displacement time graph, which is like this. The gradient gives velocity, because the gradient would be from displacement and time seconds gradient. If we divide displacement by time, we will get velocity, because that actually is previously linked here. But the area under this curve, this is just meaningless. This has no meaningless. Area under curve, area under curve. Acceleration. So velocity time graph, we will have v over meter ms minus 1 time t. If we are like this, so the gradient would equal acceleration, while the area under the curve, let's say this is a triangle, the gradient is acceleration, because this is the same as previous, as we have divided acceleration by time, velocity by time, to get acceleration, which is linked here. So next we have gradient, area under the curve. This is not meaningless here. It means it means replacement. So let's say 1 over 2 v multiply t. This will be 1 over 2 base by height. We will get displacement in an acceleration time graph. Acceleration time graph. Acceleration time graphs are very straightforward in the way that they are basically made. They can be like this, or like this. This is decreasing acceleration in a direction. This is increasing acceleration, and this is increasing acceleration, decreasing acceleration. So we have this. Next we have equation of motion. S equal v plus u 2 over t, which is displacement, is given by adding initial and final velocity divided by 2 multiplied by time. We have v square plus u square plus 2as. We have s is equal ut plus 1 over 2 at square. And we have these three equations here. We also have we have all of these here, and we have linked these together. So let's talk about projectile motion, which directly uses these equations. Projectile motion. Projectile motion, which is basically motion in basically object is basically, let's say, at a height of at a building. Let's draw a building. This is a 30-meter tall building, and a ball is thrown, and it goes in a horizontal velocity, which is this. This is the displacement s, and this is 5 meters per second. ball and it falls down here at 0 meter, and the vertical distance it travels is 20 meters, and this can we find out through this. We will not talk about this much. I will also do past papers where I will show the rest of the stuff. Okay, so this is done. Let's talk about which is linked here, like God, dynamics. Dynamics, which is study of dynamics is study of motion related to forces. Force is basically is rate of force is rate of change of momentum, or rate of change of momentum per unit time. This is also the second law of motion, that the force applied in a body is directly changed to its rate of change of momentum. Second law of motion. Second law of motion. So yeah, dynamics, second law of motion. First law is a body stays in its state of uniform motion unless its resultant force isn't, unless its resultant force isn't zero. I have 11% battery, so let's finish this. Sorry for making this all messy. That's just a reason. So let's according to this, we have something called inertia, which is basically directly proportional to mass and basically the property of an object to resist a state change of uniform motion, inertia. For the second law of motion, we have momentum, which we have talked about. Momentum is basically mass multiplied by velocity. If that was further multiplied by t, it would give x force, but let's not talk about that here. Mass multiplied velocity is momentum. A momentum, basically a body is moving like this and it's another body. For the principle of conservation of momentum in a closed system would be that its momentum would stay conserved. Like if this is 2m and with 10 meters per second, and this is 4m and 0 meters per second, this would move by 5 meters and this would also move by 5 meters. Like it would, let's say if we have m1, the equation here is m1 u1, m1 u2, m2 u2, m2 u2 is equal plus m1 v1 plus m1 v2, which is 2m 10 meters per second plus which is 0. So the momentum here is 0. So let's say this is 20 mv is equal to let's just draw here 2m, this 5, and let's Actually, let's do this 1 meters per second and try to find, the momentum that would be there. 1 v. This is my high momentum 2m, and this 4m v is equal to unknown. So we will have 24 mv is equal to 9 mv plus 4m v unknown. So basically we will 14 mv for, like we divided here 4, which will give us v. V is basically as 14. Let's just leave it here. You can just get the gist of that. So next we have third law of motion. अब when body A acts, अगर एक when a body A acts on body B, body B also acts on body A in the opposite direction, but with equal magnitude of the same type of force. Basically, if this is acting like giving basically let's say basically is applying a force of 10 Newton in this direction, then this will drive 10 Newton in this direction. This is the Newtonian laws of physics. Though if you study later, in university or in higher levels, you will basically know that this is not all like Newtonian laws of motion do apply to macro things, but at the quantum level things are very different, which will not be discussed here. Okay, third law of motion. Next to third law of motion we have let's say third law of motion, we have weight and mass. So for a layman who is not educated at all, sorry if that offends anyone, weight versus mass not same. Weight is basically the gravitational field strength of large body such as earth. Let's throw earth here. That's a very bad earth, but who cares? So it is 9.81 Newton for 1 kg. So if an watermelon of 3 kg watermelon, let's throw it like a watermelon, is dropped here at some height, so it will have some weight, which will be 9.81 multiplied by 3 kg. So let's just leave it at there. For in a round decimal, let's just make it 30 Newton. Versus mass. Mass is basically the amount of matter, which you already know from O levels or early on, which is very obvious. Mass is that, but mass stays same in the universe regardless of where you are, unless the sum of the mass is reduced by cutting a watermelon, then it will be less, but that is not specified here. So stays same regardless of position on the universe. It stays same regardless of position. So let's just continue on with this. So we have this mass, and let's talk about types of forces that will be discussed in this chapter. Types of forces. Contact force, which is basically the force that is between like for example my tablet is on a table, so the contact force of these two are acting against each other and keeping each other keeping the tablet on the table, otherwise and there's contact force, gravity. Basically gravity in Newtonian physics, we have gravity is basically if body A acts on body B using gravity, like a body, like this is body A is a ball and this is the earth. That is, it will act like this and the earth will make it act like this. So they are directly proportional to its distance, and directly proportional to mass, inversely proportional to its distance. Yeah. So we also have upthrust, which is basically the force that acts on a body due to its density, like due to if a upthrust force due to density, force due to density difference, density difference. Force due to density difference. So let's say we have for this liquid has 1500 kg per meter cube density, then our body is with 750 kg meter, so this has less density than the liquid. So sorry, then it will float. So it will float. This is given by PmG, which is density multiplied by PVG, which is basically another form of mg but in water. Since if you multiply density by volume, we will get mass, and gravitational field strength is just g. So it will give this will give the amount of force that acts on the body. Also we have viscous force, drag force, which is basically friction in water or another liquid with the particles, basically prevent oppose upthrust and make a body like if our body is falling, like it has more density, then upthrust will not be zero, upthrust will not be as strong, so it will basically fall down and keep falling down and until it reaches the bottom. So this is about here contact forces, upthrust, momentum. Let's talk about momentum, which is related to these things. Momentum, sorry if I am being very awkward, I'm just trying to get as much done as possible. Momentum is basically a quantity of mass and multiplied by volume, basically a measurement of how a body is moving and how much mass it carries to basically affect other objects in relation to that momentum. We have momentum in a conserved system. Law of conservation of momentum, law of conservation of momentum. Law of conservation of momentum, we have, which we have already studied. Next we have momentum elastic collisions plus inelastic collisions. Elastic collisions are those in which momentum mv plus m1 or 2 mv square or kinetic energy is conserved both, and in elastic collision only momentum is conserved. So basically we have these two, then we have momentum in collisions in 2D, basically where we have to use vectors to find out the total resultant momentum of a collision. Basically if a body hits a body like this and the body moves here, we will basically take this, we will basically take if this is 60 degree, then we will 60 we will basically use resolution of vectors using sin and cos x. Then next we have deformation. Deformation is basically when when a tensile, which is basically a force that enlarges when a tensile, when stress is applied on a solid, when stress is applied on a solid, and it deforms and it changes shape or volume, and it changes shape slash volume, maybe one, maybe both, it is called deformation. Deformation. And stress is applied on a solid and it changes shape or volume, it is called deformation. When stress is applied on a solid and changes shape or volume, it is called deformation. Okay, there are two types of stress: tensile, which is basically like if let's say we have this pipe with this stretchable pipe, and if we apply force like this is tensile because length is increasing, and so will volume. But if we have like on the same pipe we have a force like this, on the like this, this is compressive because it is compressing it, it's decreasing the length but increasing the cross sectional area, over here it basically cross sectional area is decreasing, massive cross sectional area is increasing, length is decreasing. So we have discussed till now. Let's discuss about how this is okay done. So compressive, so if we have length is increasing tensile, let's go further down here and talk about let's say we have a hook like this, and it basically has a weight of 5 Newton, cross sectional area of 0.15 centimeters square, and basically extension of 5 centimeter of extension of 3 centimeter, which is basically how much the force stretches it and it basically pulls it down, and how much from the original length. Let's say original length is 5 centimeter and extended length after this is 8 centimeter. We minus that and we get extension. So we will do 5 over 3, which we will now put into the calculator, which is 1.666 something, 1.6 ek. This is the constant. Now from this we can get, it has no value because it cancels out. It actually does have a base quantity which is related back to the previous topic, but we will not discuss it. Just called the K constant, force over extension. So basically if we have a force like this, if it goes straight like this, then we have, it's obeying the Hooke's law, which is said that the force is directly proportional to the extension. Like they are basically proportional, they are increasing steadily with each other. But if we, let's say it starts going over here, then the Hooke's law is broken, then here it plastically deforms. Here it is deformed, but if it returns like from here, it returns to this, then it is basically an elastic object. Otherwise, if it doesn't return and it returns like this, basically the extension is very still in a large amount, then it is an inelastic object, which is plastic deformation, and that is elastic deformation. Okay, we have done till now. Let's talk about strain, which is basically, related here. Strain is basically the amount of, for the original length, or original length divided extension divided by original length, which is basically strain. Basically, like this is related back to this and this, because it is exactly what it measures, how much, the area is changed, how much the length has changed of the object. Strain, if we know stress and strain, if we divide them both, we will get the ratio of Young's modulus, which is basically how the ratio of how much a body stress changes length in comparison to the stress applied. This is different for all materials. Like if copper has a different Young's modulus, metal, iron has a different Young's modulus, steel, so on, tungsten, everything, like that. If we talk about like this, then elastic collisions stress. So let's say we have, okay, we have discussed till now. I'm kind of thinking what to say next. Young modulus. So we also have, the, let's say we have these. Let's say we have like these hooks, like this hook here, this hook here, like this hook. No, like this hook is attached to another hook, like two hooks, and a weight of 10 Newton here. So basically the extension, the K constant would be divided between them. It would be 1 over K. It would basically be divided amongst them. This is in series. This is different how two circuits work, because of how, stress strain are different from circuits. They are entirely different things, but this is a common mathematical idea you can take from both of them. And if we have them in parallel, basically it will be equal. The stress applied over them would be equal. Let's say we have this, body that basically like this, and this is parallel because they are parallel to each other. These are parallel to each other. These would be equal, like k1 here, k1 here, k2 plus k2, or otherwise here would be 1 over k equal to, because this is divided, 1 over k1 plus 1 over k2. These are divided here. Okay, so we also have strain energy. Basically, if we talk about compressive, which is basically the more so consistent with itself, strain energy, which is either two forms, 1 over kx square, or 1 over fx. because if we have f 1 over kx is basically fx multiplied by x. So we can derive this and have this idea. Strain energy is basically elastic potential energy, or strain energy is basically the energy in a spring when it is stretched. Basically we have a rubber band, we stretch it, then it has strain energy, but if we release the stress and it bounces back, then the strain energy is transferred into kinetic energy and so on, sound energy and all that stuff, all that jazz basically. So we have discussed till here. Let's talk about uh, torque, movement torque. Torque is rate momentum. Torque is basically F into D, or movement of a force, movement of a force, which is basically the turning. Oh, this is actually not, yeah, it actually, yeah, but this is also the same term you would use for something like, work power energy, but we'll first a movement of a force, turning effect. Basically if you have this, if let me turn on the brightness, I'm very sorry, you might have a sign of holding it down. Torque F into D, moment of a force, turning. So if basically we have this, like this thing, a nut, and this is a bolt. So basically if we move it like this, let's say anti-clockwise, then it turns and it moves it, and basically it contains a turning effect. But if we have, let's, and we have principle of movements, which is basically related to equilibrium principle of movements. Basically a body is in equilibrium, equilibrium if sum of clockwise movement is equal to anti-clockwise movement. Sum of anti-clockwise equal to sum of anti-clockwise movement. So principle of movements. Next we have, couple, which is basically a derivative of this, but it acts on a circle. Like we have this force here, it only pushes in the circular direction. It will depend on the radius d or diameter d of a circle, and it will basically like a car. This is a car handle, steering wheel, and it basically is moving, and it's being like here. Turning effect. We have dynamic equilibrium Static equilibrium. Dynamic is basically uniform motion, a body staying in its uniform motion, then with zero resultant force in a static state of rest, basically. And center of gravity is basically where all of the gravity seems to act of our body. This is, of course, related to all of this fact because without center of gravity, if we have like body of like being having like a clockwise and anti-clockwise acting on it, basically the center of gravity may play a role into how much equilibrium the body has if it isn't in equilibrium, or maybe in equilibrium due or not to the center of gravity of the body. Next we have work power energy. Work power energy. Work is if a body if a body is basically a force acts on a body and the body moves in the direction of the force, then work is done. Energy is basically the transfer of ability of work to be done. Basically there are forms of energy: kinetic, kinetic energy, kinetic energy, sound energy, and sound energy, elastic potential, which we have already studied. Elastic potential energy, the kinetic energy we also discussed a bit in momentum. Elastic potential energy, elastic potential kind of sound energy, elastic potential energy. This is one of, and gravitational potential energy. This all relates to one energy form is transferred to another form. Kinetic, we can have sound, elastic, or any of these can never be created or destroyed. Energy can never in a closed system. Basically the whole universe is a closed system. There is no other thing, as we know scientifically, that exists other than the universe. So energy can never be created or destroyed, rather from one can never but only transformed, but only transformed from one form to another. So we have energy efficiency, like this is basically a measurement of how much our industrial ideas of energy are efficient. Like this can be important for you knowing how do we basically measure how much and of thing, basically how much energy we how much cost efficient our energy conversions are, so we can better have more energy efficient system, let's say, that transfer more energy from one form to another and give us more energy back. Energy efficiency and power. Efficiency is basically energy total energy output total energy output, energy input, the input, useful output, useful output multiplied by 100. This is the formula. So power, we at the end we have power, which is rate of work being done per unit time. Power F into D over T. So we are done till now, and let's meet